Today we're exploring something, well, truly groundbreaking. A concept that could really revolutionize energy storage as we know it. I mean, pushing far beyond anything currently on the market. We're talking about a fascinating new proposal called the Magnetohydrodynamic Redox Cascade Battery System, MHD-RC for short. Our mission today. Let's unpack the core challenges facing current batteries and then really dig into how this radical new system proposes to overcome them. It might just enable a future of energy we've only dreamed about.
And that future, yeah, it couldn't come soon enough. Energy storage is just so critical for the global energy transition, absolutely vital. And while, lithium-ion batteries have certainly dominated, they definitely come with fundamental limitations, things we just have to address if we're serious about powering everything cleanly.
Okay, let's unpack this then. What are the biggest pain points? The real bottlenecks with today's batteries, especially lithium-ion?
Well, there are several core challenges, really. First off, safety risks. That's a major one. We're talking about flammable organic electrolytes, which can lead to something called thermal runaway. Essentially, a cascading internal overheating. And unfortunately, we've seen some pretty high-profile fires, in grid-scale storage and
Right,
EVs.
so these aren't just small issues, they're serious safety hazards.
Exactly. Then there's energy density, how much energy they can actually store for their weight. Current batteries, they're typically around, say, 250 to 300 watt-hours per kilogram, we/kg. And honestly, they're getting pretty close to their theoretical limits. And that's just not enough for some of these emerging needs like uh, electric aviation, where weight is everything, or for truly extended range EVs, the kind that could really match gasoline cars.
So we're kind of hitting a ceiling there
Yeah,
on how much energy they can pack in.
we really are. And alongside that, you've got slow charging and degradation. Big problems for usability. These issues often stem from what are called solid-state diffusion limitations. Basically, ions just move slowly through the solid parts. And if you try to charge too quickly, you can get these things called dendrites, forming little needle-like structures. They can grow inside the battery and cause short circuits. Not good. And this directly impacts lifespan. Typical batteries might only last 500 to maybe 1,500 charge cycles before they really start to degrade.
And I guess the materials needed for these batteries, that's another growing concern. Supply chains, ethics.
Absolutely. Resource constraints are looming large. We could see potential shortages of lithium, cobalt, nickel, especially as electrification ramps up globally. And cobalt supply chains, well, they raise some pretty significant ethical and environmental concerns about how and where it's mined. So you add all that up, safety, limited performance, short lifespans, resource issues, it creates real economic and sustainability challenges. It really does call for a fundamental reimagining of how we store energy to tackle that whole energy storage trilemma, density, safety, and sustainability. And, well, that's precisely where this MHD-RC battery concept comes in. It's pitched as a really fundamental shift. We're moving from, passive ion diffusion, how current batteries work, with ions just sort of slowly moving around, to active energy conversion using controlled fluid dynamics.
Active conversion, like moving from a still pond to a flowing river, maybe.
That's a great analogy, actually. Yeah.
Here's where it gets really interesting then. So what are these revolutionary concepts? What makes this so different from, a regular battery?
It really brings together four core ideas. First, there's the liquid metal cascade. Instead of a solid anode, this system uses low melting point alloys. Things like Na-K, that's a sodium-potassium mix, or Gallium-STAN, which is gallium-indium tin. These are actually liquid at or near room temperature.
Right.
And they flow. They act as the anode, but because they're flowing, the surface is constantly regenerating, which completely eliminates that dendrite formation problem we talked about. Huge for safety and lifespan.
Wow, okay.
And crucially, these materials, sodium, potassium, gallium, they're much more abundant than lithium or cobalt. So it tackles the resource scarcity issue head on.
So a constantly renewing liquid electrode instead of a solid one that degrades. That is a big departure. What's the second concept?
Second is multi-stage redox extraction. So imagine you have sequential reaction chambers. Each chamber has a specific electrolyte, maybe oxygen in one, chlorine in another, sulfur in a third, designed to react with that liquid metal. Each stage basically harvests electrons, but at progressively lower energy potentials. It's like squeezing more energy out in steps.
Okay, so you're not just getting one reaction. You're getting multiple bites at the apple, pulling out more energy from the same metal atoms.
Exactly. This cascading design allows for near-complete oxidation of the metal. We're talking potentially extracting up to maybe 3 times more energy per atom compared to a single-step process like lithium intercalation.
3 times. That sounds like it could shatter those theoretical limits you mentioned for traditional batteries.
That's the potential, yes. The third concept is MHD energy conversion. MHD stands for Magnetohydrodynamics.
Right. Bit of mouthful.
It is. But the idea is fascinating. You take these ionized electrolyte metal slurries, the liquids carrying charge, and you accelerate them using pulsed magnetic fields. This motion, this kinetic energy, is then directly converted into electricity. It uses Faraday's law, the same principle behind electric generators.
So wait, it's not just storing chemical energy, it's converting motion directly to electricity within the battery itself.
That's the idea. And the key thing is this bypasses the usual resistance limitations you get with solid electrodes. It could enable truly immense discharge rates. The projections are for over 50,000 watts per kilogram.
50,000.
Mhm.
That's incredible power delivery. For context, what was lithium-ion again?
Typically 250 to 340 W kilograms, so it's orders of magnitude higher. Crucial for heavy industry or anything needing massive, instantaneous power bursts.
Staggering. Okay, what's the fourth concept?
Finally, there are integrated capacitive meshes. These are basically 3D nanomeshes made of graphene and emacene.
Emacene. That's one of those new 2D materials, right?
Nice.
Super thin,
Derek.
super conductive.
Exactly. These meshes line the reaction chambers. Their job is to provide immediate capacitive energy capture during those discharge pulses. Think of it like a built-in supercapacitor. It allows for millisecond-level response times, which is perfect for power smoothing dealing with the variable output from renewables, for instance.
So you have the main battery for energy, the MHD part for massive power, and these meshes for lightning-fast response. It's like combining multiple devices into one.
Precisely. It's a very integrated approach.
Okay, this all sounds amazing, almost sci-fi. Let's try and ground it a bit.
Yeah.
How does this projected performance stack up against good old lithium-ion? You gave us the power density. What about the other key metrics? Right, let's lay them out. Energy density. Li-ion, we said, maybe 150 to 300 with ERC.
Right.
Projections are 800 to 1500 with ERC.
A huge jump, up to 5 times potentially.
And power density, just to reiterate, Li-ion at 250, 340 weathicargrams versus MHD-RC at a staggering 20,000 to 50,000 weathicargrams.
Yeah, the difference is just enormous there.
Then cycle life. Li-ion, maybe 500 to 1,500 cycles before it really degrades. MHD-RC, they're projecting over 50,000 cycles.
50,000, because you don't have that same solid electrode degradation or dendrite growth.
And the big one for many people, charge time. Li-ion takes, what, 30, 60 minutes, sometimes longer? MHD-RC is projected at less than 5 minutes.
Less than 5 minutes, because you're essentially just pumping fluids back, regenerating the liquid metal quickly.
Wow. Those numbers really do shift the goalposts entirely. For you listening, think about what that means. Charging your EV faster than filling a gas tank.
Or powering entire grid sections instantly during a heat wave or a cold snap when demand spikes. It's not just an incremental improvement, it feels like a different category of technology.
So let's connect the dots. How do these concepts, these numbers, directly solve those core problems we identified earlier, that energy storage trilemma, density, safety, sustainability?
Right, let's break it down. First, the energy density revolution. How does it get to that 1,500 Wh/kg? It comes down to the chemistry, multi-electron transfer. Lithium typically gives you 1 electron per atom in the reaction. But these liquid metals, like sodium or potassium, can be fully oxidized, potentially releasing multiple electrons. Combine that fundamental chemistry advantage with lightweight cathode materials like sulfur, which has a very high theoretical capacity, around 1,675 millipog, and that's how you reach these projected densities over 1,500 Wh/kg.
5 times current Li-ion.
Exactly, making it genuinely suitable for things like electric aviation or long-haul trucking, where weight is absolutely critical.
So it really opens up applications that are just, well, difficult or impossible today because of battery weight.
Precisely. Then, ultra-rapid charging and discharging. How does that work? Well, for charging, you use magnetic pumping, basically using magnetic fields to move the fluid to reverse the flow. This quickly regenerates the metallic anode. We're talking minutes, like we said, and importantly, no dendrites form in the liquid.
Okay.
And for discharge, that MHD acceleration gives you near instantaneous power delivery. You're not limited by how fast ions can move through a solid, plus you have that capacitive nanomesh buffering the really fast peak demands response times under 10 milliseconds.
Milliseconds.
Yeah, essential for things like grid frequency regulation, keeping the power grid stable, or even just the immediate acceleration you want in an EV. It really tackles that trade-off where batteries are either good at storing energy or delivering power quickly, but rarely both. This aims to do both exceptionally well.
Addresses those two big consumer pain points. charge time, and maybe range anxiety too if the density holds up.
Uh.
What about safety?
Safety transformation is a huge focus. The most obvious thing is replacing those flammable organic electrolytes found in lithium-ion. This system proposes using aqueous water-based or inorganic ionic liquids. These are inherently non-flammable. That alone eliminates a major fire risk.
That's a big deal right there.
Absolutely. Plus, the continuous fluid flow naturally distributes heat, preventing hot spots. And they've integrated thermoelectric generators, TEGs.
Right, turning waste heat back into electricity.
Exactly. It recovers some energy and helps manage temperature. And even if there were some kind of thermal issue, the design includes pressure release channels. It's designed to manage excursions as contained flows, not dangerous explosions.
Okay.
All this makes it potentially suitable for really sensitive places, underground mining, maybe even medical implants where safety is paramount.
It sounds inherently safer by design. And the last piece of the trilemma, sustainability.
Yeah, sustainability and circularity. This is another area where it looks really promising. First, the materials. It uses earth-abundant elements. Sodium, potassium, zinc, sulfur. It completely avoids those critical minerals like lithium and especially cobalt with all its associated issues.
Big plus.
Definitely. It also features a closed-loop oxidant subsystem. So if it uses gases like oxygen or chlorine in those reaction stages, the system is designed to capture and regenerate them, minimizing the need for constant input.
Oh, more efficient.
And then recycling. Because it's a modular design with flowing liquids and separable components, they project over 95% recyclability.
95%.
Mm-hmm.
Compared to what for lithium-ion? Maybe 30, 50% currently, and often much less in practice?
Exactly. It's a huge difference, aiming for a truly circular economy approach. And on top of all that, initial life cycle analyses suggest a 40–60% lower carbon footprint compared to manufacturing and using lithium-ion systems.
Wow. So non-flammable, no critical minerals, much higher recyclability, lower carbon footprint. It really seems to tackle those environmental and resource concerns head-on, almost like a closed loop.
That's the vision. And making this all work involves some pretty advanced engineering. For instance, AI-driven reconfiguration. There's a proposed neural control system. It would constantly monitor sensor data flow rates, temperatures, voltages, and use that to optimize everything in real time. The magnetic fields, the fluid paths, the mix of oxidants.
So it's a smart battery that tunes itself.
Essentially, yes. And it gets smarter. They envision machine learning algorithms that could predict potential failure modes, maybe 10 or 20 cycles before they happen, allowing for preventative maintenance. It could even adapt its operating mode, maybe run in a high-efficiency cascade mode when demand is low, then switch to prioritizing that high-power MHD discharge when peak load hits.
That's incredible. Self-optimizing, self-diagnosing.
And the architecture itself is designed to be scalable. That's really key. You could potentially have tiny microfluidic versions, maybe using biocompatible gallium-zinc alloys, small enough for medical implants, perhaps under 10 watt-hours.
Wow.
All the way up to massive grid-scale systems, maybe using something like zinc-bromine chemistry in large flow tanks, exceeding 100 megawatt-hours, possibly sharing common magnetic accelerator units.
So from wearables to powering cities. That's incredible versatility.
It is. And finally, there's the multimodal efficiency. They project over 95% round-trip efficiency.
95%. That's better than lithium-ion, isn't it?
Yes. Li-ion is typically 85–90%, and much better than conventional flow batteries, which are often more like 70–75%. It achieves this by integrating energy pathways. The direct MHD conversion, which itself might be around 60% efficient, plus the capacitive storage, plus those thermoelectric generators recovering maybe 10–15% of waste heat. It all adds up.
So it's squeezing efficiency from multiple angles.
Yeah.
Reducing wasted energy, which is crucial for renewables, less curtailment.
Exactly. Minimizing wasted energy is key.
Okay, this all sounds truly transformative. But let's be realistic. Groundbreaking tech always faces huge hurdles. What are the big challenges here? What needs to happen to make this real?
Oh, absolutely. There are significant challenges. A major one is materials compatibility. You're dealing with highly reactive liquid metals at potentially elevated temperatures. They can be quite corrosive. So you need advanced containment. We're talking things like special ceramic laminated steel for the chambers, maybe protective graphene coatings, those atomically thin, super strong layers. Finding materials that are durable and cost-effective is a big engineering task.
Right.
And the electrolytes need careful formulation too, precise buffering to prevent unwanted side reactions that could degrade performance or components. Research is looking into things like ionic liquid solid-water hybrids with special additives.
So material science is key.
Hmm.
What else?
MHD efficiency optimization, getting that direct energy conversion part working efficiently is critical. The main enemy here is fluid turbulence, which wastes energy. So a lot of work involves computational fluid dynamics, basically. Computer simulations to design the chambers just right, maybe tapered designs, vortex suppressors, and you need very powerful magnetic fields, likely from superconducting magnets, maybe in the 15-20 Tesla range. For comparison, a hospital MRI is usually 1.5 to 3 Tesla.
Okay, serious magnets.
Very serious. Initial prototypes are apparently achieving around 45% MHD conversion efficiency, but the target is to push that up towards 70%. Still work to do there.
And integrating it all.
Exactly. System integration and control complexity. You're bringing together reactive fluids, powerful magnetic fields, complex electrochemistry, nanomeshes, AI control. Making all those pieces work together reliably, safely, and seamlessly is an immense engineering and software challenge.
No doubt. So assuming these challenges can be overcome, what's the roadmap look like? How might this actually reach the market?
Well, the proponents have outlined a potential commercialization roadmap on roughly 3 phases. Phase 1, maybe 2026 to 2028, would be about proof of concept. Perhaps a simpler single-chamber system using sodium-potassium and maybe hydrogen peroxide as the oxidant, targeting an application like drone propulsion. Something to demonstrate the core tech.
Okay, starting smaller.
Then phase 2, say 2029 to 2031, might focus on developing dual cascade grid modules, maybe around 100 kilowatt hours in size, incorporating that AI control. They'd likely partner with industrial players, perhaps for niche applications like electrifying mining operations.
Testing it in demanding environments.
Exactly. And then phase 3, looking out to 2032 and beyond, that's when you'd aim for the full multi-cascade systems, targeting those big applications. EV aviation, large-scale grid storage, really leveraging economies of scale as the manufacturing matures.
So a stepped approach over the next decade or so.
That seems to be the plan. It's ambitious, for sure, but if it works, the MHD-RC battery really could, as I said, transcend conventional energy storage paradigms. It's less like a box passively holding charge and more like an electrochemical engine that actively processes energy.
Electrochemical engine. I like that. So wrapping this up, what does this all mean for you, the listener? Well, this system seems to tackle that trilemma we discussed: energy density, safety, and sustainability all at once, which is something current batteries really struggle with. If this pans out, it could enable things we can barely imagine today. Sub-minute EV charging feels revolutionary enough, but think about terawatt-scale storage to buffer entire continents' renewable grids seasonally. And the broader impact, it lines up perfectly with global goals for decarbonization. The source material we looked at suggested it could potentially displace maybe 30–40% of lithium-ion applications by 2040.
A significant chunk.
A huge chunk, enabling a fossil-free energy future where storage isn't the weak link, isn't the bottleneck holding back renewables. It really prompts a rethink of our entire energy infrastructure.
Absolutely. And maybe a final thought to leave you with. Just imagine for a moment, what if energy storage wasn't really a limitation anymore? If it was abundant, safe, ultra-fast, long-lasting, and made from common materials, what kind of world would that enable? How would it change transportation, grid stability, even our concept of energy independence? What new possibilities open up for our shared energy future?